Today, we're going to work on the first of two special factorizations that we're going to do. Today, we're going to work on perfect square trinomials. All right, trinomials, three terms, that are perfect squares. So we need to know what perfect squares are. So we're going to factor perfect square trinomials, and then we're going to solve quadratic equations where we can factor in this manner to help us solve the equation. All right? Now, our perfect square trinomials will be in this form right here. This doesn't necessarily need to make sense to you at this moment. It needs to make sense to you in a little bit, okay? By the end of the day, for sure. That needs to make sense to you. Right now, it may not. And let's talk about perfect squares. Forget about factoring for a minute. What is a perfect square? And I don't mean the geometric figure. What's a perfect? That's right. It's a number that has a whole number square root. It's something squared. I wrote that it's a number squared. I started to literally write something squared. But it's a number squared. So you're familiar with lots of perfect squares. You really are. Okay? All you got to do to make a list of perfect squares is start at 1 and square it. Well, what do you get when you square 1? 1. So 1 is a perfect square. And then square 2. 4 is a perfect square. Square 3. 9 is a perfect square. So got these? The last one I wrote down was 13 squared. You need to be familiar with all of these. Will this list think you're at the end? All you got to do is add 1 to the... Got a new one. So the perfect squares never end. Okay? Now, these are all whole numbers for squares. You can have perfect squares that are fractions as well. For instance, you could take 1/2 and square it. You'd get 1/4, wouldn't you? 1/4 is a perfect square. You could take 1/3 and square it. You'd get 1/9. 1/9 is a perfect square. Look, it gets worse. You could take 2/5 and square it. 4/9 4/25 is a perfect square. So there's lots and lots and lots of fractions that are perfect squares. Notice this, and it's a small list, so you may not be able to pick up on it. For a fraction to be a perfect square, the numerator is a perfect square, and the denominator is a perfect square. Whenever that happens, the fraction is a perfect square. Now, we're going to deal almost exclusively with whole numbers, but recognize those, okay? Now, we can also use decimals, and we're not, but you can do decimals. All right, it's a little awkward. Now, 1/2 as a decimal is 0.5. So if I square 1/2 as a fraction and get 1/4, if I square 0.5 as a decimal, I'm going to get the decimal equivalent to 1/4, aren't I? Okay? And you can take something weird. You can take 0.46 and square it. So 0.2116 is actually a perfect square. Now look, nobody recognizes that because you'd have to memorize. Well, you can't. You can't memorize all that, okay? But you got to realize that those exist. And like I said, we're going to work almost exclusively with whole numbers. Now, one thing I want you to notice, every number in our list, whole numbers, fractions, decimals, perfect squares are always positive, aren't they? Because a perfect square comes from squaring something. Whenever you multiply a number times itself, it's never negative, is it? Because positive times positive is positive, negative times negative is positive. So perfect squares are never negative. Okay? Now, let's get to our perfect square trinomials. Let's take, and you don't have to even write this part down. Let's take a binomial and square it. By definition, whatever square that is a perfect square, correct? Number squared, in this case, a number where we don't know what the A and the B are, squared, by definition, my result is a perfect square. Now, to square anything means to multiply it times itself. So that's A plus B times A plus B. Use the FOIL method. And you get A squared plus AB plus AB plus B squared. Combine like terms, and you get A squared plus 2AB plus B squared. So that is a perfect square. I cannot spell trinomial. What if it's a minus sign between the A and the B? Well, to square that, by definition, whatever my result is a perfect square. Let's figure it out. That'll be A minus B times A minus B. FOIL method gives me A squared minus AB plus B squared, which when I combine like terms is A squared minus 2AB plus B squared. So that's the other form a perfect square trinomial can take. Notice the first term is positive and it's a square. The last term is positive and it's a square. The middle term can be positive or negative, and the middle term has to be, and this is awkward to say, so listen, the middle term has to be 2 times whatever you square to get the first term of your trinomial times whatever it is you square to get the last term of your trinomial. A is whatever you square to get the first term. B is whatever you square to get the last term. Since this, watch me now, since this in red leads to this in the blue box, doesn't that mean if I start with the blue box, I know that its factorization is this in the red box? It's got to be, right? So we're going to memorize that that's the way it works. Okay? Let's see. Now I'm having a hard time making my mind what I want to do next. I'll just go with what I've got. First, let's work on recognizing a perfect square trinomial when we see it. Okay? Now, just because all of a sudden you've been taught what a perfect square trinomial is, does not mean that every trinomial you see from this day forward is a perfect square trinomial. Some of them are, some of them aren't. A perfect square trinomial is in this form, right? Like I had here, a squared, either a plus sign or a minus sign, 2ab plus b squared. Now I expect that to make sense to you. So it'll either be a squared plus 2ab plus b squared, or to be a squared minus 2ab plus b squared. Okay? 3 conditions have to be met for it to be a perfect square trinomial. Because if you try to factor something as a perfect square, but it's not a perfect square, you won't factor it right. So first condition is pretty easy. The first term, the a squared, has to be something squared. It has to be a perfect square. Second condition is easy. The last term has to be b squared. It has to be a perfect square. The hard part, the middle term, the bx term, has to be 2 times whatever was squared to give you the first term times whatever was squared to give you the last term. And that's the hardest one to check. Well, it's the one students tend not to check, which leads to problems. Okay? So, let's try these two examples to recognize whether or not we're dealing with perfect square trinomials. For question A, says, well, for both of these, determine whether each trinomial is a perfect square trinomial. And here are the questions you ask yourself to determine this. First, is the first term a perfect square? Is 4y squared something squared? Yes, it's what squared? 2y. So, yes, it's 2y squared. Okay? What about 9? Is 9 a perfect square? Yeah, that one's a little more obvious. It's 3 squared. Is the middle term equal to 2? Now, it's not 2 times 2y squared times 3 squared. It's 2 times a, which is what we square to get our first perfect square. So is it 2 times a? What would b equal? What do I square to get my last term? 3. See, it's not 2 times 4y squared times 9. That's not the question. Is it 2, what you square to get 4y squared, which is 2y, times what you square to get 9, which is 3? Is it? Yes. So, yes, yes, yes. Is this a perfect square trinomial? Yes. Now, I'm going to start calling things A and B because it's simpler to talk about. Since a squared is 2y, a is 2y. Since b squared is 9, b is 3. So is the middle 2ab? Is the middle 2 times 2y times 3? The answer to all those things is yes. So here's how you factor a perfect square trinomial. Remember, we started with this and we ended with this. Take it backwards. We just proved to ourselves that we have this 4y squared plus 12y plus 9 is a squared plus 2ab plus b squared. So the factorization is simply a, what's a? 2y plus b, what's b? 3 quantity squared. Okay? Now, I'm going to ask you a question that I wish you didn't know the answer to. Could I factor that without knowing it's a perfect square trinomial? Could I factor it using the AC method? Yeah. Then why are we doing this? Faster. It's much more efficient if you can recognize it. You got to get good at recognizing it, but it's much more efficient. All right, let's try B. All right, is the first term, is 9x squared a perfect square? Yes, it's what squared? 3x. So A is 3x. Is the last term, 4, a perfect square. So B is 2. So we're just doing the negative one. Is the negative one 2AB? Or is the middle one negative 2AB? Is it negative 2 times 3x times 2? It's not. So that one's no. No, it's not a perfect square trinomial. That doesn't mean you can't factor it. I haven't worked this one out. Maybe you can still factor it with the AC method. Maybe you can't. If you can, factor it. If you can't, you put prime. Okay? All I'm worried about right now is the perfect square part. Y'all with me? All right, let's do number 5 here. Write this example down. We've got x squared plus 22x plus 121. Is the a perfect square? Yes, it would equal x, wouldn't it? Is the last term a perfect square? Yep, b would be 11. 2 times x times 11? Yes, this is a perfect square trinomial, which means its factorization is a, which we said was x, plus b, which we said is 11. Quantity squared. We're done. Move on to the next one. Look at number 6. I don't like number 6 because they need to rewrite that. Make it j squared plus 18j plus 81. Is that one a perfect square trinomial? What's a equal? J. What's b equal? 9. So is the middle 2 times j times 9? Yep. So what's the factorization? That's it. Okay. Let's try one a little more difficult. Let's say 14. On 14, is 16a squared a perfect square? It's what squared? 4a. So a is 4a, right? It's a little confusing. Is 25b squared a perfect square? Yeah, it's 5b squared. So a, is the middle, and that's negative, but that's okay, is the middle negative 2 times 4a times 5b. Negative 2 times 4a times 5b. Is it? Yes, so this is a perfect square trinomial. What goes first in our parentheses? 4a b, quantity squared. What's the sign in between those two terms? Negative. So it's a negative 2a, so it's negative. Now, let me point a few things out. The first term must be positive. The last term must be positive. The middle term can be positive or negative as long as it's 2ab. Okay? And if the middle term is negative, then the sign in your binomial is negative. If the middle term is positive, then the sign in your binomial is positive. Okay? Now, that's worth knowing. Okay? It really is. All right. Do that one. See what you get. You got it? Did you get what I got? Any questions? Okay. Let me show you something kind of neat. To solve a quadratic equation, we've always had to have them equal to 0. because we've only used the zero product property. Look what happens on these two. I could, on both of these, square the binomial, on 4a, square the binomial, whatever I get, subtract 121 from both sides, and then solve the equation the way we've been doing it by factoring, using the zero product property. But, and we've done this quite a bit this year, can't I take the square root of both sides of an equation? I can. What do you think the square root of a minus 10 quantity squared is? It's a minus 10. It's got to be. The square root of a quantity squared is the quantity. What do you think what is the square root of 121? Boom. Easy one to solve. Okay? Even if the right side's not a perfect square. Take the square, for 4b, take the square root of both sides. What's the square root of z plus 3 quantity squared? Z plus 3. Square root of 26, I'm just going to call the square root of 26. Subtract 3 from both sides. And then, depending upon the situation, maybe I typed it in my calculator and maybe I don't. Neat, huh? Now, I got a question. On all the other quadratic equations we had, I got 2 solutions. Let's just look at the one with numbers, easier to think about. Anybody got a clue why I might just get 1 solution there? That's right. Both our factors are the same, aren't they? Look back at what we've already done. Both our factors are x plus 11. So look, if there was an equals 0 at the end of that, I've only got one factor, x plus 11, to set equal to 0. Negative 11 is my only solution. Okay? Make sense? Now, technically speaking, quadratics do always have 2 solutions, but what you'll learn later on is that those solutions do not have to be unique, meaning they don't have to be different. Technically, x plus 11 quantity squared is x plus 11 times x plus 11. So when we solve that, we would get negative 11 twice. Do you need it twice? No, you just need it once. So you would get 2 solutions. They're just not unique. They're the same. But that's for another day.